Okay. Okay, so just to review, we're just discussing when is a finitely generated group big. We've decided the finite groups are small and probably the integers are small. How about another example, Yongchuan?
Z2.
Okay. So if Z is small, how could Z2 suddenly be big? Let's just try that. Catherine, do you have a thought?
Okay, I was gonna say like a group that has exponential growth should be big.
Okay, interesting question, interesting point. So explain to us what exponential growth is.
So like if you look at the Cayley graph for a group, then if you look at like balls around an element or like around the identity, then you can look at like how fast those balls grow.
In terms of the number of elements they contain.
Yeah, yeah.
Okay, so that's a great idea. So since I've already mentioned graphs, let's recall the notion of a Cayley graph. So if G has a finite generating set S, so it's generated by S1 up to Sn, then you can form what I'll call the Cayley graph of G with respect to this generating set S. This is a graph, and the vertices of the graph are just equal to the elements of G. And then we draw an edge between G and let's say GSI for all I. And in other words, you connect two elements of the group when they differ by multiplication by a generator. And you'll notice that one of the nice things about this graph is I'm only putting the SIs on one side. That's important when the graph is not abelian. And now when the graph actually admits an action of G. G acts on the graph by multiplication on the other side, on the left, and it clearly preserves this edge condition. So G acts by automorphisms of this graph. So G acts here. And also, if we make each edge of length 1, then the graph turns into a metric space. And in particular, it gives you a metric on the group. And the distance of a group element from the identity is what in this metric? Somebody other than Catherine want to say?
Is it like the number of the smallest number of generators you need to get to the element?
That's right. It's the shortest word in the generators that expresses the given element. It's the length of the shortest word. So that's a nice idea, is that the distance from the identity to an element G is the length of the shortest word in our generators. That represents, let's say that satisfies W is equal to G. So a word is an expression in S's and their inverses. Usually we'll assume that if S contains a generator, it also contains its inverse. A word is just then a product of generators, a formal product of generators, and then when you multiply it out, it actually represents an element of the group. So many words represent the same element, and the shortest word is the distance of the element from the identity. Okay, so then we can look at the number of elements in the ball around the identity of radius n in G with respect to this metric. So I've forgotten the graph for a minute, but I kept the metric. And in fact, prior to Cayley, people certainly studied this idea somewhat less geometrically. They just said, look at all the elements you can express with words of length less than or equal to n. And this function might grow slowly or it might grow rapidly. For example, if we take the integers, with the generator 1, then the size of this ball is roughly n. For Z2, it's roughly n squared. But there might be groups where it grows exponentially fast. It can't grow faster than exponentially because the number of words of length n is bounded by the number of generators to the nth power. So this is big O of the number of generators to the n. So it can grow at most exponentially, and if it actually does grow exponentially, we say the group has exponential growth. So that's a nice idea. That's as fast as the balls can possibly grow, and so we might put those over here. Groups of exponential growth. Okay. Actually, Mary, you're next. Do you have a group to suggest?
Oh, I was going to say a free group, but that's covered by this example on the right. I mean,
that's okay. We're allowed to put specific cases of, you have to check for any individual group whether or not what its growth rate is. In fact, there exist groups whose growth rates are not known. So here, Z star Z, this is the free group on 2 generators, say A and B. And for this group, if we take A, B, and their inverses as our standard generating set, then the group looks like this. You have the identity, and then you have A. And now here's an important lesson in combinatorial group theory. You never write A inverse. That's too complicated and confusing. Instead, you write A bar. And then it takes up the same amount of room as A. So here's the inverse, A bar, B, B bar. And now we have to be a little bit careful about whether we're multiplying on the right or the left. So A is attached to AB by my convention, because you can multiply by B, and B is attached, but it's also attached to I should have put A squared up here. It's also attached to AB, and it's also attached to AB bar. And similarly, if we look at reduced words, that is, we never have an element followed by its inverse, then each time we make the word longer, we have 3 choices for the new letter that we add. So you can see that the ball of radius 1, the circle of radius 1 rather, consists of 4 elements. The circle of radius 0 consists of 1 element, and then the circle of radius 2 consists of 3 times 4 elements. So Bn in this case is 1 plus 4 plus 4 times 3 plus 4 times 3 squared, all the way up to 4 times 3 to the n minus 1. Which of course is approximately, it's on the order of 3 to the n. So we do have exponential growth. The growth rate is about 3 to the n for this generating set. Now you might know there's a nice theorem that the free group on 2 generators contains as a subgroup every free group on any number of generators. In fact, topologically, that's sort of obvious because the free group corresponds to the fundamental group of a bouquet of 2 circles, and this is covered by more complicated looking graphs. For example, one that looks like this, and the fundamental group here is a free group on 4 generators. And so there's certainly, and of course the pi1 of a covering space is a subgroup of pi1 of the base. So there are free groups of arbitrarily large rank inside of here. That's just to say that the growth rate depends very much on the choice of generators, and it's not like the growth rate of subgroups is less than the growth rate of the original groups. It all depends on what you choose as generating sets. Okay. Let's see who we're up for. Rohil, do you have a group to suggest?
I was thinking maybe an interesting example for big groups is surface fundamental groups.
Yeah,
although it's very similar to the free group example because you're
it's
just
similar,
doing
but
one
it's
relation.
it's certainly not a free group when the surface is closed. So that's interesting. So let's look at surface groups. Actually, there's the fundamental group of a surface of genus G. When G is 1, that's Z2. That's the torus. So that's small. But on the other hand, if G is greater than or equal to 2, then this is the fundamental group of a hyperbolic manifold. It feels like that negative curvature is associated to exponential growth, and in fact it is. The fact that the balls of radius r in hyperbolic space have volume that grows like e to the r implies that any group, the fundamental group of any compact hyperbolic manifold has exponential growth. So if we're going to throw exponential growth in here, then we certainly need to include the surface groups for G greater than or equal to 2. What's another argument that the surface groups belong on this side?
If you have estimates for like number of geodesics, because there's one geodesic per homotopy class.
Yeah.
That's the way I was thinking of it. Yeah.
How about
There's
someone
like,
else? Can you suggest an argument why the surface group of genus 2 should be on this side?
Well, they contain free groups.
Yeah, that's right. So this contains a free group on 2 generators, and so you maybe if a group is big, and then any supergroup is even bigger. Okay, so I see some people have not raised their hands. So does anybody? Here we go. Somebody raised their hand for just a second. Michael, do you have a group to suggest or a thought to add to the discussion?
I guess, well, this is probably kind of silly. I mean, I guess you could say any abelian finitely generated group is small, probably.
Sure, that's good. I like that. So abelian groups. Now, of course, an abelian group that's finitely generated is isomorphic to z to the n cross a finite abelian group. Still, that's starting to indicate that maybe there are certain constructions in groups that preserve the size of groups. Does somebody else have a group to suggest? How about suggesting a principle that these notions of smallness and bigness should satisfy? Like an axiom that they should ratify. I mean, I'll give you one that's been suggested already, and that's been used implicitly on both sides. So we might ask that if G is big and G is contained in H, then this implies H is big. Which of course also means that if H is small, then G must be small. So in other words, the notion of bigness and smallness behaves correctly under inclusions. What's another construction in group theory that we might ask preserves or behaves in the right way with respect to bigness and smallness? Michael.
Maybe a quotient of a group by a small group.
So what would you say? What would the principle be?
Like a big group quotiented by a small group might be big.
Ooh, interesting. So you might ask that big divided by small is big. That's interesting. What's another? Somebody else tell me another quotient principle that might make sense.
Quotient of a small group is small?
Yeah, right. So is small modulo anything should be small. It's even smaller. And so consequently, to put it differently, if you take a big group, if a quotient is big, then the original group was big. Yeah, this is kind of interesting. Okay, now can somebody describe a notion in group theory that involves both subgroups and quotient groups?
Short exact sequences.
Our TA comes to the rescue. Yes. So there's a general notion, of course, of an exact sequence of groups. Since the groups are non-abelian, I'm going to write it with 1. So 1 goes to A, goes to B, goes to C, goes to 1. This is an exact sequence of groups. So what might be a good statement about the relationship between the sizes of these groups? So we already have one relation, which is that if A is big, then B is big. So if we're interested in figuring out what we can say about B, we already kind of understand what we want to say. And we've also decided that if C is big, then B is big, because that's this quotient statement. So can we make one statement that includes both those and applies to a general exact sequence? Well, let me throw out a suggestion. If B is made out of copies of C and A, the simplest exact sequence is when B is the product of C and A. Now, under what circumstances do you expect the product of two groups to be small?
If they're both small.
They're both small, right? So let's generalize that to exact sequences. After all, B is just a twisted product of A and B. So one possible property we might like our groups to satisfy is that if A is small and C is small, then this implies B is small. Okay, let's suppose that we have our notion satisfies this property. What can we add to our list of groups? What groups can you build out of the existing small groups that are not already on this list?
You can do semi-direct products, I suppose.
Okay, so sure. So semi-direct products of what though?
Anything on the prior list.
Okay, so semi-direct products here of these things. Let's forget the finite groups for the moment, because the finite groups, having a finite group here or here, it doesn't change the group very much. It kind of modifies the Cayley graph by only a finite amount. So let's forget about that for a moment. So what groups can we build up from abelian groups by taking exact sequences?
Solvable groups?
Solvable groups. So let's be a little bit more precise here and say solvable groups should be small. Because if abelian groups are small, well, every solvable group can be put into an exact sequence of smaller solvable groups until you eventually get down to an abelian group. So the smallest category of groups that includes the abelian groups and is closed under the formation of these B's is in fact the solvable groups. And by the way, let me just remind you that the nilpotent groups are special cases of solvable groups. And actually they behave a little bit differently than the solvable groups geometrically, so they're good to keep in mind. Let me remind you what a nilpotent group is. So if you have a nilpotent group, then G should have a non-trivial center. The center is the elements in G that commute with everything. And so once you have a center, you can take G and mod out by the center. And you get a new group. And this group might now have a new center. And so you mod out by it, and you keep going, and then eventually you get an abelian group. In other words, you get a group that's its own center. So nice examples are, for example, the Heisenberg group. It's generated by elements A, B, and C, where the commutator of A and B is C, and C commutes with everything. Okay, so that's another class of groups that are small. Okay, so what we are going to do is we are now going to invent a notion of big and small groups such that all of these statements are correct, except for one. One is slightly off. So what is suspect here? Does anybody know? There's actually an inconsistency on the board at the moment. And I don't fault anyone for this inconsistency. It's a subtle point. So the inconsistency is the following. It will turn out that big groups are contained in the groups of exponential growth. However, there are groups of exponential growth which, somewhat surprisingly, don't deserve to be called big, at least not by the axioms that we've proposed so far. And in fact, there exist solvable groups that are of exponential growth. So that's a minor correction we have to make here. Exponential growth is in fact going to be a consequence of being big, but it's not going to be enough to prove a group is big. So who can give me an example of a solvable group with exponential growth? Or even an interesting example of a solvable group? I'm sure people know examples of non-abelian solvable groups. So how about an infinite one?
Unipotent, upper triangular unipotents with like integer entries.
In what group?
Oh, in like SLNZ?
Okay, so let's be careful. So you want to have something like 1, 1, 1, star, star, star. Is that right?
Yeah.
And it's, let's say, contained in SL3Z. Yes, so I'm worried about, I think this group is the Heisenberg group. Am I right about that? You should.
Oh, yeah.
So actually this group is nilpotent if you take integer entries.
Mm-hmm.
And I think the central element must be where you have 0 here and here, and then something just there. In any case, this group does not quite have exponential growth. But there is a way to get solvable groups with exponential growth in a fairly routine fashion. And let me give you a couple of examples to convince you that solvable allows rather untamed groups. So one example of a solvable group is a semi-direct product of abelian groups. Now, how do you form a semi-direct product let's say, of Zn with Z. And by the way, I never know which way this sign is supposed to go. So maybe somebody can tell me. So what I want is to say the way this semi-direct product works is we take a map from Z into the automorphisms of Zn. And so, so our semi-direct product admits a map to Z with kernel Zn, and conjugation by the elements of Z acts on Zn, since that's a normal subgroup, and that action is given by this automorphism. That's enough information to recover what the group is. So in fact, it's uniquely determined once you know how conjugation acts, given that it's a semi-direct product. And what are the automorphisms of Zn? What is the automorphism group of Zn? It's nice, simple abelian. Simple. It's not simple. This nice elementary abelian group. Ben, you look like you know.
SL and Z?
Almost.
Reflection?
I mean,
Or,
minus the identity is not an SLNZ when n is odd.
yeah, okay, yeah. Yeah.
So, I mean, that's a minor nuance. The automorphism group is what's usually called GLNZ. And of course, what this means is not the integral matrix with non-zero determinant, but the integral matrices whose inverses are also integral, which means they have determinant plus or minus 1. So the determinant is plus or minus 1. And of course, this such a matrix just acts by A applied to a vector V in Zn. That's the automorphism. P of A of V is AV. Since these are integers, you stay within the Zn lattice. And then this requirement shows that it's actually an automorphism because it has an integral inverse. Or put differently, the fact that the determinant is plus or minus 1 implies that this map is surjective. The determinant up to sign is actually the index of the image of A of Zn inside of Zn. Okay, so this has a big automorphism group. And so to construct this semi-direct product, we just need to pick an element in this automorphism group. And the simplest case is when n is equal to 2. And so we're picking an element in GL2Z. As Ben hinted, it barely makes any difference whether we work in GL2 or SL2. So, well, SL2Z is a group we know very well by now. And there's 3 types of elements in SL2Z. There's elliptic, there's parabolic, and there's hyperbolic. So if we're given an element here, A in SL2Z, we can then attach to it a group, GA, which is Z2 semi-direct product with Z, where the Z acts by this transformation A. And what do you think happens? Well, if A is of finite order, then GA is virtually abelian. In other words, you can pass to a subgroup of finite index, that's what virtually means, such that A becomes trivial, namely, only consider the generators here, the powers that are a high power here, high enough that A to the n is equal to 1. So we have this map to Z, if A to the K is equal to the identity, then inside of here we take KZ, we take its preimage, and we get a subgroup which is the trivial product between Z and Z cross A. So there is a subgroup a finite index that's just C3. What happens if A is parabolic? For example, what if it's 1, 1, 0, 1? What kind of group do we get? Anybody want to just take a guess? The type of group we get is on the board somewhere.
Oh, is it the Heisenberg group?
No,
No, not quite.
but it is a nilpotent.
Nilpotent.
Right. So the point is that if we take the inner product with a parabolic element, then A applied to the vector, let me just call it E1, in other words, the vector 1, 0, is equal to E1. So multiplication by A commutes with E1, addition by E1 also commutes with addition by E2. So the subgroup generated by E1 here is central. And as a consequence, this group is nilpotent. And I should say, by the way, it's a nice exercise to show that nilpotent groups share with abelian groups the property that they have polynomial growth. So I mentioned we're going to see that big implies exponential growth. And so that's one way, one of the nice features you could look at in this group. It turns out this group has polynomial growth, and so that's another indication that it's relatively small. However, it turns out that if A is hyperbolic, then this GA has exponential growth. And so if you take the semi-direct product with 2, 1, 1, 1, you'll get an explicit solvable group of exponential growth. So that's the classification of what happens when you form these semi-direct products. So these are all small, but they exhibit 3 different types of behavior: virtually abelian, nilpotent, and exponential growth. Well, I didn't prove they have exponential growth. So, but it's not hard to believe, because you see, if you take A to be 2, 1, 1, 1, then A to the n has entries that look like they have something to do with the Fibonacci series, something like this. So the entries in A have exponential growth. So when you apply A to the n to a vector 1, 0, you quickly get very long vectors. And then by taking linear combinations of those very long vectors, you get exponentially many elements in your group. But I'd like to give another example of a solvable group with exponential growth that's more elementary and more transparent. So here's a example 2 of solvable plus exponential growth is we take the group G sitting inside the group of affine transformations of the real line. So these will be maps of the real line to itself of the form x goes to ax plus b. Right? Provided A is not equal to 0, that's a group. And we're going to take the subgroup generated by the transformation A of x is 2x, and the transformation B, where B of x is x plus 1. And I claim that G has exponential growth. Okay, and let's see why. So the basic point is that something interesting happens when you conjugate A by B, B by A. So let's look at what A inverse B at A of X is. So we take X and we double it, then we add 1, and then we multiply by 1/2. And that gives X plus 1/2. So if we call this B0, let's call X plus 1/2 to the K, let's call this BK. And what we find is, by the same token, A to the minus K, B, A to the K is X plus 1/2 to the K. In other words, it's this element, BK. So if you conjugate B n times, you end up with translations that are smaller and smaller and smaller, and they're converging to the identity. So if we were to take the ball around the identity of radius, let's say n plus 1, or actually let's say 2n plus 1, this would contain B0, B1, all the way up to Bn. Because the length of this word is 2k plus 1. And now, notice that we can then take the product B0 to the E0, B1 to the E1, up to Bn to the En, where each EI is 0 or 1. And what does this give when applied to X? It gives X goes to X plus E0 plus E1/2 plus E2/2, E2/4 plus En/2 to the n. And of course, all of these elements are distinct. So after we've built these elements, if we take n plus 1 further products, we get 2 to the n different elements in our group. So the ball of radius E of, so now I took n plus 1 more of radius 3n plus 1. The size of this is certainly greater than or equal to 2 to the n. And therefore, the group has exponential growth, and yet it's solvable. Okay, so this is a not uncommon and interesting phenomenon that solvable groups, although they're very amenable to concrete study, especially semi-direct products like this, semi-direct products of abelian groups, they're quite easy to study concretely. They give rise to really interesting and complex Cayley graphs, in particular Cayley graphs with exponential growth. Okay, so actually what we're going to have is not that exponential growth just discriminates between these two sides. It turns out that the growth rate of the Cayley graph, while interesting, will not be a robust notion of big. And the reason it's not a robust notion of big is because of exactly this. Here, we've constructed a group with two generators, and or let me go to the previous example. We have this Z2 semi-direct product Z over A. When A was hyperbolic, we had an abelian extension of an abelian group, and we got to a group of exponential growth. So small growth for A and B is not enough to ensure small growth for A and C is not enough to ensure small growth for B. So what is a robust notion of a group being big? And that notion is called amenability. So amenability will be a kind of warm-up to property T, or rather non-amenability will be a notion of bigness, and then property T will be sort of an even bigger notion of bigness. And that's what we will use to construct expanding graphs. Okay, so here's our list. Now comes the definition. A group G is amenable, and in terms of our previous discussion, this will mean small, if there exists a G invariant mean, M from L infinity of G to the real numbers. Equivalently, if there exists a G invariant measure, probability measure on G. Okay, now this is a little bit crazy. Suppose I said I want a group with a G invariant probability measure on it. Well, that probability measure has to assign positive mass to some element in the group because the group is countable, being finitely generated. But if it assigns positive mass to some element, it has to assign the same mass to every other element because the group, it's an invariant measure. And therefore, the group is finite. Otherwise, the total mass of the group would be infinite. So this is a little funny. This is, in fact, the right definition, but here we have to put in the word finitely additive. So this probability measure, mu, behaves just like the ordinary probability measures that you're familiar with on groups, except it's not countably additive, but it is finitely additive. If you have finitely many disjoint sets, the sum of their measures is the measure of the sum of the union, and it has the property that mu of G is equal to 1. Okay, so let me explain the first definition in more detail. So first, what is a mean? A mean on any set, such as the set G, is a linear map on the space of bounded functions, which gives you, so to speak, the average of the function. So to say it gives the average just means it satisfies a couple of axioms. So the axioms are the mean of the constant function 1 should be equal to 1. So among the bounded functions, there's the one that's 1 on every element of G. And the second property, which corresponds to positive measures, is that if you have a function f of G, which is greater than or equal to 0 for all G, then this implies the mean of f is greater than or equal to 0. So as you know,
sorry, one question. Yeah. When you write L infinity of G, what measure are you using for?
Oh, good question.
L infinity of G.
So first, L infinity doesn't require a measure. So G is a discrete group. Right? So
okay.
This is just an abstract set, but it's a very good point. Why am I calling it L infinity? It's kind of weird. All I mean is functions f from G to R such that the sup over G of the absolute value of f of G, that's the L infinity norm of G, is finite. So bounded functions on G. But you're right, implicitly, I will be talking about the measure on G that gives mass 1 to every element of G. So I'll also be interested, for example, in L2 of G. And these will be functions where the sum of f of G squared, that will be the norm of f in L2 squared. So when I talk about LP spaces, it's respect to this obvious, so to speak, hard measure on this discrete group, normalized so every element has mass 1. And that shouldn't be confused with this funny measure here, which will somehow be a probability measure on an infinite set. In fact, the measure of every individual element will be 0, but the measure of the whole set will be 1. Okay, so let's back up to this definition. So a mean is just something that assigns a number to every L infinity function. And notice that f, see what this property here says is that if f is bounded above by 1 and below by 0, then its mean has to be between 0 and 1, right? Because 1 minus f would then also be positive. So if you combine linearity and these two axioms, what you find is that the mean of f, which should be thought of as some sort of average value, the mean of f lies in the interval between minus the norm of f and the norm of f in L infinity. And in fact, if f is a positive function, then it lies between 0 and the supernorm of f, if f is positive. Okay, so what's the associated finitely additive measure? Oh, and by the way, I should say that because of this, because the m of f is bounded by the L infinity norm of f, these two axioms imply that this is a continuous linear map from the L infinity norm to the real numbers. So we can put continuous here. So it's an element of the dual Banach space to L infinity of G. And finally, if we have a mean, it gives rise to a measure in the obvious way. If you want to know the size of a set, you take its indicator function and then you ask what the mean is of that function. So the mean of the indicator function of set is used to define this measure of the set A. And then this is finitely additive because of the fact that mu is linear. So the sum of the indicator functions of the AI equals 1 to n. If these AI are disjoint, then by linearity, if we let f be this, linearity, mu of the union of these AIs is the sum of m of the indicator function of the AIs, which is the sum of the measures of the AIs. Now, why doesn't this work for countable additivity? So if we had countable additivity here, and these AIs were disjoint, and let's say the AIs are all non-empty, then no reason to include empty elements in this union. If these AIs were all non-empty, and we took the partial sum from 1 to n of the indicator functions of AI, and then we subtract off f, we would just get the sum of the indicator functions of the AIs for I greater than n. And so the L infinity norm of this would be equal to the L infinity norm of this, which is equal to 1 because some of these AIs are non-empty. So in other words, in L infinity, these finite sums do not converge to the infinite sum. And that's why this measure is in general not countably additive. And by the way, a lot of people talk about the invariant means without any reference to this measure, but it's sometimes convenient for intuition to think of the invariant means in this way. Okay, so now the problem that you're presented with by this definition is how would you ever know if a group has an invariant mean? Well, I'm advocating this as a notion of small groups. So the groups that we've described as being small had better have invariant means. So let's just check that they do. So some examples of amenable groups. So first, finite groups. So in this case, Oh, I didn't say what G invariant means, but obviously, so for this measure, to say that it's G invariant means, well, we can consider either the right or the left action of G on itself. Let's take the right action for fun. So to say it's G invariant is to say that the measure of A times G is equal to the measure of A for all subsets A in the group and for all G in the group. That's what invariance means. In terms of the mean, well, there's an action of G on L infinity. So G dot f of x is f of gx for f in L infinity. And then we want that the mean of G dot f is the same as the mean of f for all f and G. That's what it means for the mean to be invariant. So in other words, you have a way of averaging functions, and if you shift the function by the group action, at least on one side, the mean is invariant under the group. So of course, if we have a finite group G, we can just set the mean of f to be 1 over the cardinality of G, the sum of the values of f and G. Okay, no big deal. The interesting case is the case of the integers. The integers turn out to be an amenable group. And at first blush, you might say, well, that's pretty easy. If you have a bounded sequence, you just take its limit. And we'll call that will not depend on shifting the function along. And that would be a good definition of the invariant mean on the integers. But there's a couple of problems. For one thing, the limit might be the same in different directions, plus or minus. Oh, well, so we'll take the limit in the positive direction. But what are we going to do with sequences that don't converge? Well, there's some sequences where it's not hard to guess what the mean should be. So for example, suppose we take the sequence 0, 1, 0, 1, etc. on the integers. So this is my function f with its values on the integers. What is the mean value of f?
A half.
It's a half, obviously, because it's half the time 1, but half the time 0. But in fact, that's not just an intuition, it's a theorem. Because you see, if you take f and your group Z is generated by, let me call it T for translation, then T dot f is the sequence 1, 0, 1, 0, etc. And the mean of f and the mean of T dot f have to agree. But when you add up f and T dot f, you get 1, 1, 1. So since the mean of f plus Tf is equal to 1 by the axiom that the mean of the constant sequence is 1, the mean of f has to be a half. But there's still a problem, which is what if your sequence starts out with 10 zeros, and then 100 ones, and then 1,000 zeros, and then 10,000 ones, and so on. What is the mean of that sequence going to be? There's good arguments that it should be 0, good arguments it should be 1, good arguments it should be something in between. And we're faced with the problem of assigning a mean consistently to every single bounded sequence, and not only that, making sure that it's shift invariant. So how can we possibly ever define this mean on all bounded functions on Z? Well, the answer is we can't. But just because you can't define something doesn't mean it doesn't exist. We can appeal to one of the non-constructive axioms in mathematics, namely the axiom of choice. And we appeal to it implicitly through Tikhonov's theorem, or more precisely, the version of Tikhonov's theorem that's used to show that in a Banach space, the unit ball in the dual space is compact in the weak star topology. So let me remind you, let's compare this to something we did earlier which is we showed that if T from X to X is a homeomorphism, and T is compact, then there exists a T invariant measure. Probability measure on X. So T is acting on the space of continuous functions by pullback under this homeomorphism. And there's an induced action on the dual of the space C of X, which is the space of signed measures. And contained in here was the space of probability measures. That space is also preserved by T. It's convex. And then what we did to produce a T invariant measure was we started with some measures that were almost T invariant. Namely, we took 1 over n times the delta function at x plus the delta function at tx plus the delta function at tn minus 1x. And then we took the limit as n goes to infinity. But the problem is there's no reason to presume that that limit exists. But there's a basic theorem that says that in the weak star topology on C of x, that is in the topology where mu n tends to mu, if and only if the integral of f mu n tends to the integral of f mu for all f in C of x. In the weak star topology, the space of probability measures is compact. And the proof of that theorem depends on the axiom of choice. So what we did was we then passed to a convergent subsequence. And then mu n tend to mu. And then since these measures mu n are becoming themselves more and more nearly invariant, this limit measure was literally invariant under T. So T mu is equal to mu. Okay, so we can do exactly the same thing for the integers. What we do is we define a sequence of means. So this is the theorem. I just turned 2 into a theorem. Z is amenable. And the proof, in brief, is let Mn of f be the average of f at 0 plus f of 1 plus f of n minus 1. And now what you'll notice is that this, this Mn is almost invariant. If the L infinity norm of f is equal to 1, then when we take f and we shift it by translation, that is, we move, this is this t here. If we change f of g to f of g plus 1, or f of n to f of n plus 1, we just change this sum by the first and last term, each of which is bounded by 1. So mn of tf minus mn of f is less than or equal to 2 over n. Exactly the same argument we used here. And now we use the fact that the unit ball is compact again. But instead of the continuous functions on x, we use L infinity of g. And the mean is a linear functional at L infinity of g, so it lives in L infinity of g star. And then within here, we have the means. These are the means, and the means are defined by convex conditions. So this is in fact a compact convex set, again with respect to the weak star topology. And then we take a sequence of probability measures, except they're only finitely additive. That's basically what these MNs are. And then we pass to a convergent subsequence. And the limit of that convergent subsequence is our invariant mean. So pass to a convergent subsequence, Mn goes to M, and this limit will be G invariant. Okay, now here's a little something that I should highlight for you, which is that this dual of L infinity of G is an enormous space. You'll know when you study Banach spaces, you talk about the dual of LP is L cubes, for example, on the real line or on 0, 1, or on the integers. Except the dual of L1 is L infinity, but the dual of L infinity is not L1. L1 is not a reflexive space. The dual of L infinity is some enormous space that people usually don't talk about. And what it is it's the space of finitely additive measures on the integers or on the real line. So in any case, we're dealing with it, we're confronting it here. And this space is not just not equal to L1, although it includes L1, but it's not separable in general. And it's not metrizable. And it's not first countable. And what that means is that the topology on this space is not well adapted to sequences. If you don't have a countable base at a point, then at every point, then you can't form the closure of a set by taking all convergent subsequences. You have to use more sophisticated objects, which are called nets. So I'll just mention this as a little bit of analytic nuance that is required to do these arguments correctly. So it's not true that every sequence has a convergent subsequence. What's true is that every sequence has a convergent subnet. And nets are like sequences, they're just indexed by more complicated partially ordered sets rather than the integers. So you can pass to a convergent subnet Mn sub alpha. And alpha ranges in this partially ordered set. There's still a notion of convergence, and it's still true that the limit exists and is G invariant. Okay, so buried in this construction is the axiom of choice. And basically, the means agree on the well-defined sequences, well-behaved sequences, and then you have to make a choice each time you encounter an ill-behaved sequence. And once you've made that choice, it predicates a lot of additional choices, but you still have a lot of remaining choices to make. And the axiom of choice asserts that you can make all those choices consistently. So this is a very powerful definition. But when we're using it theoretically, it works very nicely. But you want to convert it into something that you can see more transparently. Nevertheless, it will satisfy the conditions we want. So we proved that examples of amenable groups, we have that finite groups are amenable, and we just proved that Z is amenable. Now here's a couple of other assertions. So if G is amenable and G mod n is equal to H, if we take a quotient group, then H is amenable. And this is very easy because you have a map from L infinity of H into L infinity of G. Just take a function on H and consider it as a function of G that happens to be constant on the cosets of n. And then you already have a mean here. And so you use that to give a mean on L infinity of H. So indeed, when a group is small, all its quotient groups are small. It's also true that if H is contained in G and G is amenable, then this implies H is amenable. And here you're faced with a slightly different problem. What you do is you write G is equal to the disjoint union of some cosets, HGI. And now if you're given an F in L infinity of G, of H, you turn it into an F in L infinity of G, by setting capital F on GI of H to be the obvious thing, namely F of GIX is little f of x. Okay, so what you do is you take your group and you write it as a disjoint union of copies of H. You have H itself and x1H, x2H, etc. And then when you have a function on H, it gives rise to functions on all of these cosets. And the way it lifts to L infinity of G is not canonical. It depends on the choice of these coset representatives. Sorry, these should be G's. Nevertheless, you can now take your mean on G, and that gives you a mean on H. Finally, these last two observations are summed up in the more general result, which we formulated, which was that if A and B are amenable, sorry, A and C are amenable, and we have an exact sequence, 1 goes to A, goes to B, goes to C, goes to 1, then B is amenable. And the proof of this is somewhat similar and easily understood by a picture. So what you do is if you're given an F in L infinity of B, you take B and you again write it as a union of cosets of A. And remember, these cosets are exactly the fibers of the map. This is B. These are the fibers of the map from G to C. And so if we have a function f here, we can now replace it by a function that's constant on these fibers. Namely, we take the function on A and we replace it by the mean of the function over A. That will be a number that we then make constant along A. So replace f restricted to GIA by the mean over A of the function f translated by GI inverse, so that it becomes a function on, translated by GI, so that it becomes a function on A. So that gives us a function that's constant on these fibers, and therefore it gives a function, a map from L infinity of B to L infinity of C. And here we already have a mean MC. And so we take, roughly speaking, we take F to MC of MA applied to F. And that gives us the mean on B of F. Okay, so average over the fibers, then average over the base, that gives you an average on the total space. That's great, because once we have this, we then can conclude 6, that solvable groups are amenable. Okay, so what's most assuredly important is to know that there are non-amenable groups. And you guys have already hit that target on the nose. The prime example of a non-amenable group is the free group on 2 generators. So there are lots of nice amenable groups, but the free group is not. So the theorem is Z star Z, free group on AB, is not amenable. And the proof of this is very nice. So it depends, it's nicely expressed in terms of measures. So we look at the Cayley graph, A, B, B bar, A bar, etc. So the part of the Cayley graph, and then we have over here this was AB, AB bar, A squared. Okay, so so this part of the Cayley graph, let me call that A. See, the Cayley graph naturally splits into 4 parts. We might call them A bar, B, and B bar. These are the words that begin with A, the words that begin with A bar, the words that begin with B, and the words that begin with B bar, and then there's the identity left over. Now, if you have an invariant mean on an infinite group, it has to be 0 on every group element. Because if it were positive on one group element, it would have to be positive on every group element, and that would be a contradiction. So note, mu is G invariant probability measure, and G is infinite, then mu of any individual group element is equal to 0. Although mu of the whole group is equal to 1. So mu of the identity is equal to 0. But mu of the whole group is equal to 1. And here we've written the group as the union of 4 disjoint sets. And since the measure is finitely additive, the measure of one of these sets has to be positive. Otherwise, the measure of the whole group would be 0. So by changing our choice of generators, we can assume that the measure of A is positive. But now here's the great idea. Suppose you take A and you multiply it by AB bar. That gives you a copy of A inside of itself, AB bar A. The words that begin with AB bar is a subset of the words that begin with A. And similarly, the words that begin with AB is a subset of the words that begin with A. But these 2 sets are disjoint. And if this measure were to be translation invariant, the measure of this set and the measure of this set would have to be the same as the measure of A, because they're both contained in A. So the measure of A would have to be greater than or equal to twice the measure of A. And of course, that's a contradiction. Okay, so that's why the free group is not amenable. It's because you can take a part of the free group and put 2 copies of it inside of itself. So it's not possible to define a reasonable measure on subsets of the free group, whereas somehow it is possible to define a reasonable measure on subgroups of Z. And in turn, you can't take the integers and decompose them into 4 sets and then take one of those 4 sets and put 2 copies of it inside of itself. So it's this decomposition property, this so-called paradoxical decomposition, that leads to this being non-amenable. And by the way, this is the same phenomena that underlies the von Oktarsky paradox, which says there's no rotation invariant measure defined on, say, all subsets of R3. Okay, so we'll return to amenability next time, describe it much more geometrically, and then move in the direction of representations in property T and expander graphs. Okay.